let's see, we're on 13, right? And then 14, yeah, ignore 14 for now. 14, there's nothing to do, yeah. Usually I update them like right before class. Yeah, I should close down 14. Oh, yeah. Yeah, I've got a bug where it's opening like too many days fast, but oh well. Thank you. Let's see here.
My dad's going to New York, so I'm like, let's go to New York, steal his car, drive home, drop him back off to New York. Like, I'm done.
Wait, what happened?
Alrighty, folks. Good to see everybody. We'll go ahead and get started here as folks are coming in. Kind of a fun pre-class warm-up just to get us going here. Continuing on with the theme of what we were talking about last week, with component pattern, and sort of getting into entity component systems, which is like a data-driven way to develop your games. So you can read ahead of this. I might post this article again later, but it's from a studio that basically took a custom game engine that was being developed by Autodesk. So if you used any 3D software, there's a good chance it could have been Autodesk, I guess. But they talk about sort of their data-oriented design. So we kind of talked about having game objects and putting components into them. This article does a nice job talking about, well, how do we kind of rip out those components and just associate them with integer IDs, right? That's sort of like the lowest, like the smallest thing that we can do if we're going to organize an engine. So anyways, it has some nice stuff. We're going to talk about this stuff later regardless, but I thought it'd be nice to take a little bit of a preview and again always kind of see what are their pros doing, what do professional engines look like. We've got a few game engine studies coming up where we're going to dedicate some class time to just reading some source code and just kind of digging around, because I found that's very useful to just again see how things are done before you get into your projects. So anyways, that's a little bit on the pre-class warm-up, so feel free to check that out after class if you haven't already. Let's go ahead and look at our logistics, just where we're at here. Module 13. We might get into some scene management stuff, but I think we're going to spend most of our time on the math today. But otherwise, coming up, we have, I'm going to release the online exam on Canvas on Wednesday. And, there's a little study guide here as far as what's going on there. So I'll go ahead and open that up. That should be open. Basically, it's a list of topics you can kind of go down and scroll through it as you need. But the main thing is, as far as exam logistics, maybe it's best to look at it here. So the exam's going to open up on the 9th, and then you need to complete it by the 14th anywhere on Earth. So, before you go on break, basically. And basically what that means is just finding 75 minutes, in a quiet place to open the exam. Once you open it, you'll have time to complete it from there. Again, the exam's designed to be pretty reasonable. If you've been following along in class, it's just a sort of check to make sure, are you understanding and absorbing some of the concepts? So if you go through the study guide, you could even copy and paste this and make a cheat sheet from this. Just kind of listed some of the topics that I thought that were important regarding graphics, patterns, things we've programmed. I'll add a little bit of the math stuff that we've talked about today. Again, just to make sure you're absorbing that stuff. So, it should be an exam you can kind of think through. And again, short answer, multiple choice stuff there. So any questions about the exam? I'll remind you and go over the logistics again on Wednesday once it's opened up. Again, it's not something to, hopefully super stress about, but prepare a little bit. It's a good opportunity, again, mid-semester or around mid-semester to just go ahead and do a check-in on yourself of how you're understanding stuff. All right, any questions about that? All right, and then otherwise, PSET 6 was released. I think I ended up releasing it at some point on Friday. So that's some math stuff. It was growing pretty big. The programming part, actually, PSET 6 should be pretty fast to implement as far as you're going to be doing some vector math exercises, basically building your own little library there. There's some unit tests to test it against, and once it's working, you'll actually see something in the next part, some like visual demonstration of it working. So that's for PSET 6. PSET 7, which I'm going to plan to release tomorrow. In some ways, it's kind of a nice one for me because I'm just going to kind of let you loose, and well, there'll be a little bit of implementation with some of the math stuff we're going to talk about, but I'm going to just basically tell you to build a game, of like Space Invaders, basically. So you get to be let loose a little bit there. So that's going to be coming up again, probably. And since that'll be, sort of a game project, I'm not going to have anything obviously due during your fall break, but after. So you have a little bit more time. If you want to work on stuff during fall break, that's your decision. But you'll have a little bit extra time for PSET 7. Questions on upcoming logistics otherwise? No? All right, great. Well, let's get into it. We're going to talk about a little bit more math. If we have some time, we'll talk about scene management. I'll expect that might push into Module 14, but got some more essential goodies to talk about as far as the game engine is concerned here. Again, there's just our logistics. But where we were last time, so again, talking about this component pattern, again, and this is where things kind of get exciting to me because we're putting things together into, finally having this pretty flexible game object primitive, right? And we talked about how we could pack in different components to give different powers to our game object, meaning if we want an animated sprite, we could have an animated component, maybe a transform to position it. We could have a collider, which we talked a little bit about circle collision here, and we just, as we need things, put that into the game object. And then what we're able to do is have the functionality or the actual logic sort of isolated into those components in some effort to, one, avoid coupling our code too much, especially as our projects grow large, and again, two, just have the flexibility of not having one monolithic game object with everything. So that was the idea, or primary sort of idea with the component pattern. And then we can, once we have individual components, then we can also think about designing systems around those components as well. We'll just need a way to keep track of them, which is where we're going to kind of keep moving towards as we move forward here. So that's what we were looking at last time. We also visited a few other just important systems-y topics like atomics and how to do things atomically. So like setting the game object, for instance, was an example of that. All right, so where we are in the engine, again, we're going to talk about some matrix mathematics. So again, this is more linear algebra stuff. We just got to kind of know here. And then again, that'll kind of lead us into scene management stuff. Hopefully, well, probably next lecture, I think is when we're going to get to it realistically. If you end up taking a graphics class with me in the future, we'll see. That's in the works. Basically doing something similar to what we're doing today, except in 3 dimensions. So we're going to look at it in 2 dimensions first. It's actually kind of nice. I kind of wish I learned it this way because 2D is a little bit simpler, but the principles are the same. So hopefully this will be a good crash course into some of the math, or I know some of you have done some of the linear algebra stuff, but again, see how to apply it in a game context here. So anyways, we've been talking about transformations previously, or at least a little bit, when we were talking about vectors, right? This idea that we could have 2 vectors, we could add them, and if we kind of put a point at the end of a vector, we'd end up somewhere, right? If I said fly to Boston and then fly to Toronto from Boston, you'd kind of, draw some arrows and just kind of figure out where you land here by adding those 2 directional vectors together. So that was the basic idea of what we talked about last time in our one of our math lectures. And then we also sort of ended with this idea of, I said, well, it's going to be pretty nice if we can also think about if we can start thinking about different coordinate spaces. So again, if I gave you sort of a graph here, right, we sort of understand this, where we could plot a point anywhere, but fortunately for us, or maybe what seems unfortunate, is our screen coordinates are actually kind of flipped around, right, where the y-axis is growing down. One, for historic reasons, but it also just sort of makes sense to have the origin in the top left coordinate. So, we're going to want to think about working in these different spaces, whether that is the like pixel coordinates, or the screen coordinates, or our world coordinates, the 2 that we sort of talked about. and be able to sort of transform or go between those two different spaces, depending on what type of problem we're trying to solve. So we talked a little bit previously about, well, if I have my world here and I just want to view a portion of the screen here, right, we could sort of constrain it. So that's where you could see the full world sort of on the left, and then what you actually see in the camera on the right. And again, many reasons to do that, because we can't display everything on the world, right? We have to constrain ourselves. So we talked a little bit about these types of transformations, and with today, with matrices, we'll be able to perform these much more easily, or move from one space to the other. Okay. All right. So let's take a look at matrices, or we'll dive into matrices here. Basically, what we're going to talk about is just about 5 operations here that we want to fully understand how they're working behind the scenes. Then you can implement them. Scaling, rotation, translation, probably ones that you've heard of. Reflection, you could probably intuitively understand. And then a shear or a skew operation, which is a little bit weird, but it actually is one of the more fundamental graphics operations. All right, so let's look at some matrix math. So what is a matrix? Again, just something that looks like this, just a rectangular array of numbers here, or scalar values. For the most part in this class, again, we'll work with floating point values. That's pretty much all we work with in graphics, I guess. But again, it's going to be useful for us, as you can imagine, to implement some sort of data structure, just like our vector, for those of you who've looked at PSET 6, to have a matrix templated structure like this, right? So we'll kind of see this repeating theme here. Okay, so just some notation, or just to be clear, when I'm talking about a matrix here, this is a 3x3 matrix. So that means 3 rows by 3 columns here. And I have a little bit of, for those of you who can see the colors, color coding here, so you can see blue and orange here. I'll do that on a few slides, just so you can understand row and column, because it could flip. But we're going to follow a specific convention here. And typically in this class, we're going to find that we end up using 3x3 matrices for our 2D graphics. And again, if you come see me in the future in a 3D course, we're going to use 4x4 matrices, right? We'll need one extra dimension. Now we'll get to why we need 3x3 matrices in a 2x2 world towards the end. That's where we're going to hope to land today. We also primarily work with just square matrices most of the time. Of course, the vector, if you want to think of that like a matrix, that's not square, right? It's either really long, like 3 rows in 1 column, let's say. But yeah, typically we have the same number of rows and columns here, so we just call that a square matrix. Okay, and again, here's just labeling our columns and our rows. Again, I always just think of it like a Excel spreadsheet or something, where you have your columns and rows running, but there it is. And again, this is going to be our tool for doing various spatial transformations, right? So moving points around in space somewhere. And by points, again, we can think about these, if you want to think about them like every individual pixel, that's also fine. Okay, so we also want to break down our matrix into, or at least this is the nice way to think about it. All of a sudden I've got 9 values. And you might be thinking, well, Mike, we've been, working with, plotting an X and a Y point, right? That's 2 values. All of a sudden we've got 9 here. So maybe we're just complicating things. But again, if we break down a matrix, it tends to be a really kind of compact and nice tool here. So again, let's just look at this or start defining some more things. Well, if I look at this first column here, again, remember our columns here, that's got 3 values here. And we call this a column vector here. So it's 1 column, this column vector, and contains all the rows here. And again, that's sort of like a 3x1 matrix here, or 3x1 vector. That's within this matrix here. Okay, so I've got 3 column vectors that make up this one matrix. And what turns out, what this matrix is actually representing here is the first column vector here actually has to deal with operations that we're going to perform on the x-axis. Second column matrix is how we're going to perform some operations on the y-axis, so how we're going to modify in the y direction. And this last one, well, we'll get to that. There's just a little question mark here for now. But it's going to have to do with something about how we move points around in space here. Okay. So if you remember from a few lectures ago, and I think maybe I'll show some reminders, right? The big deal, or why linear algebra is kind of neat, is we can perform operations independently. Right? So I can move some point around the x-axis, or I can move it on the y-axis. I could do it in parallel, for instance. But that's the idea here. So we can think about, again, our x transformation of a point and a y transformation of a point here. All right. So again, we don't want to forget about vectors. These are our nice tools for moving stuff around still, but now we've just kind of packed them into a matrix here. So, thinking about this from a coding perspective, we can represent a matrix in the D language. Again, here's just a version with a float. You bet I'm going to give you a version that's got a template constraint in the types, and then you can have integer or floating point values or something like that. But they'll look relatively similar, something like this, right? Where we want a matrix here. We've got 9 values. And then, we'll want to think about some convenient ways to operate within this matrix, meaning how do we construct one? Again, we'll want sort of a default matrix, which I'll define in a moment. Maybe we'll want to set all the elements. And maybe we want to access all the row vectors or column vectors, okay, in different ways. So those will be kind of some of the handy operations that we'll want to do with our matrices, as well as the transformations we're going to talk about. So just from a coding perspective, if you want to get a prototype of things, that's what it's going to look like. There are some little things that we'll also want to keep in mind. Luckily, the defaults are sort of right for us. If I give you 9 values and some rows and columns, we'll want to access things efficiently. I mean, in practice, everything's going to fit in memory anyways, but that's just a little aside here. It doesn't matter, too, if you sort of think about things in terms of rows or columns or flip the order, as long as you're consistent. It just happens to be, I think, in one sort of column major way because of how I've programmed for a long time. But some of you might think in a row major way, and you can flip things around if you want. It's no problem. It's just a little aside on that. And again, the little aside on no more vectors. Now we're still using vectors. As I mentioned, right, within our matrix, right, each of these column vectors here are still important. So I'm not throwing away anything that we learned before. So don't worry about that. Okay, so let's get into kind of transforming points with matrices, start doing something interesting. And again, our goal is to just move around points. Now again, we have a quad. That's basically all we have in our 2D world, right? That consists of 4 points. And usually we're just thinking about moving the top left of that quad when we've been moving our sprites around. But either way, the operations that we might want to perform are things like translation, scaling, so making things bigger, and then we can translate again or whatever. And the way that we're going to do this, how we move points around, is by multiplying matrices. Okay, so I bet I can almost guarantee at some point you had a math class somewhere where you had to by hand, multiply a matrix or something. If you haven't, I'll show you again how to do it briefly. But that's going to be sort of our tool, matrix multiplication. All right, here's some other examples here. Here's a little solar system. And again, we just want to think about how do we perform these transformations? How do we get stuff to move around nicely? Again, going back to our previous lectures, if I have the sun and I want the Earth to rotate around the sun, right, I basically got to translate it out. I can figure that out pretty easily by the X and the Y position, but the rotation would be a little bit more tricky, and that's why we had things like polar coordinates. But luckily now we're just going to basically have a translate operation and then a rotation. So again, I can translate out the Earth, that's the third one here, in case we're keeping track, and then rotate it around the sun, right? And we can figure out clockwise or counterclockwise how we want to do this. All right, and that's basically the idea here. So matrix multiplication, that's going to be our tool. You could probably make a lot of money if you could figure out how to do this faster than other ways. There's a few different techniques for how to do this, or if you can multiply really big matrices, right? That's where all the money is being made these days in machine learning. But basically, you're doing a bunch of dot products here, And again, the way to remember this, first row, taking the dot product with the first column. So first row, first column, that gives you the entry in the first row in the first column. If I take the dot product of, say, the second row in the first column, that gets me the second row, first column. Again, you're just doing dot products over and over and over and over again to do this. You could do it in parallel. That's totally fine too if you want to challenge yourself a little bit. But that's the idea. So you can test yourself later on this if you want to see it working. Now the important thing is when we're doing multiplications, we won't have to worry about this too much because we're going to be working with square matrices most of the time, or vectors that have the same number of well, we got to match, let me make sure I get this right, the number of columns to the rows here. Okay, so in this example, matrix A, I've got 3 columns. In this matrix, I've got 3 rows, so I can multiply those, and then I get this resulting matrix here. Okay. All right. So again, here's just another visual example. Because we are going to be effectively taking some matrix here, that's going to be our transformation, and we'll have some point here, some vector like this. And again, I said you got to have 3 rows for some reason, which we'll figure out in a little bit here. And basically just make sure that the number of rows in this guy, or sorry, the number of columns in this guy matches the number of rows, so you can see those match, and that'll give you this resulting matrix here. Okay, so if you kind of line up the colors, you can see where those come from. Again, not going to be a big deal for us because we're going to work with square matrices for our matrix transformations, and then all of our vectors are going to be 1 by 3 or 3 by 1, however you transform them. All right, so the real power, though, again with matrix math or using matrices in computer graphics in our 2D games is going to be that composition power. So again, if we want to model something like a solar system or something very hierarchical like human body where the torso moves and the arms better move with the torso, we can model that in an easy way here. Now just some properties or some ways to think about this. So let's say we have, and again, I'm labeling some vector or v1 or really a point here, because kind of remember we talked about vectors and points being kind of similar, but you can think about this as a point here if you want, or a vector, it doesn't really matter in this example. But we kind of perform the transformations right to left. So this is going to be kind of the weird thing when you're writing out your code and saying, well, I want to scale something and then translate it and then rotate it. You got to kind of think backwards, right to left on this. Just the way the multiplication kind of works out here to give you the expected transformation. So here, in this example, here's my vector. I'm going to scale it, and then I'm going to rotate it. Right? So we kind of read these backwards here. All right, so that's the idea. Okay, so again, with that in mind, we're going to be reading things backwards for the semester. If I'm composing matrices, one of the questions is, does the order matter? So we're going to do a little exercise here to wake folks up here. Let me tap this carefully. All right, and the way to remember this so you never forget, or if you wonder, why isn't something showing up on my screen, if you like to participate, you can stand up. We'll do a little exercise so you don't forget. You can keep your laptop with you. Yeah, just stand up. Find a spot where you have some room to move. Maybe the aisles. And you're going to have to be a little bit careful because I tell you to walk 10 steps. So, if you want to stay where you're at, you can do like 10 really tiny steps. It's not really going to matter. And if you got your laptop in your lap and you can't move, that's fine too. But all right, so remember where you're at. Remember where your orientation is. You can stick your hand out if you're not gonna, make sure you don't run into somebody. All right, good. No injuries. And let's see. For this first example, turn to your left and do 10 steps or 10 baby steps. All right, some of you are going far. Some of you are staying close. Yeah, count them out. All right. Yeah. All right. So just make a mental note of where you're at, and then go back to where you were. I got kind of reversed now. Oh. All right, let's see. So let's see. I made you turn left and do 10 steps. Now this time you're going to take 10 steps forward and then turn left. Now some of you are stuck. That's okay. I mean, it doesn't matter if you're stuck. Just pretend you're taking 10 steps. Yeah. Some of you are going to jump the chairs, but we've got some athletes in here. All right, you have to turn left. All right, yep, Jason, you're going for it. All right, now if you followed my directions, right, you ended up somewhere different. Okay, so it makes sense, right? If you turn left and walk 10 steps, same thing in our matrix transformations. Hopefully, you never forget. All right, so thanks for stretching your legs a little bit here. Exercise. All right. What other exercises can we do today? Now, translate 100 units to the sky. No. All right. So thanks for doing that. So here it is, right? And you'll see me use a couple examples, with a clock, because you can, easily see it's changing. But with a clock face here, right? If I scale it, and squish it down and then rotate it, versus if I rotate it and then squish it down, right, you get a different operation. Even if you're like, oh, okay, like scaling and rotation, those seem like you could. No, you want to compose stuff in the right order here. The order actually matters. Okay, so just keep that in mind. When you're programming your games and something disappears off the screen, just say, okay, what order did I do it? And did I do it kind of backwards, right? Thinking right to left in my multiplication. Alrighty. So order matters. It's not commutative. Again, these are the types of things where, again, in PSET 6, I've got a little write-up about like op binary versus op binary right, and kind of how to think about that. Again, it just kind of is nice. So we can use that in our matrix multiplication so that we're always thinking right to left. So we chain things together. And again, the other analogy is just think of it like string concatenation. Right, if you think about these as strings, AB is not the same as BA. So again, that's the idea there. All right. Okay, so more examples of order mattering, and this is how you create things. If you're wondering, like, well, if I want to rotate some shape and create an order, right? That means, or an orbit, excuse me. I've got to translate it out, and then I'm rotating around the origin. And that's how I kind of create the Earth versus the Sun, which is just sitting at the origin and just rotating about its sort of local axis. Okay. All right, now how do we undo our transformations? I just told you to go back to where you were, which wasn't very, efficient, but, we have some memory. We can kind of think about these things. But we can perform an inverse, okay? This is actual, and the reason I put this on the slide is because these are the types of questions you get asked in like a graphics interview. Like, how do you undo an operation? You can say, oh, you take the inverse. Okay, so you folks are going to know, right? Versus saying like go backwards or undo or something. But inverse, it's a pretty well-defined operation. I'm just going to give it to you, right? This is, and again, for exam purposes, I'm probably not going to ask you to like derive this from scratch or something. Nothing crazy. I might ask you, how do you undo? Something like that. But inverse of a matrix basically gives you the matrix that if you multiply it by another matrix, you'll get the identity or an unchanged matrix here. So I'll talk about identity in a moment, but let's just say we've got these values 4, 3, 3, and 2. I compute what the inverse is, I multiply them, and then I get this matrix with ones along the diagonal. That's the identity. That's the equivalent of multiplying or like the number 1 in the matrix world. Okay, that's the basic idea. So to undo, there are and we'll talk about this. If, I guess it'll most likely be Wednesday. But we can also start thinking about some data structures that we know if we want to undo things. Right, we can have a stack of operations that we kind of keep track of. Okay, I rotated and then I scaled, or what we did, we walked to the left and then, turned or whatever, right? We could have a stack and kind of pop those operations off a stack too. So again, all this is stuff we know, just have to figure out where to apply it. There are some other, again, things that you've probably done at some point in your life where a teacher or somebody, some professor told you to compute the determinant of a matrix as well. Again, for 2D, it's not too bad. For 3D matrices or 4D, right, you have to do a bunch of these little 2D ones and kind of compose them. But that's basically our tool. If somebody asks you what it's for, is to tell you, can I basically do this undo operation? Right, and you can kind of clearly see if I have 1 over the determinant, right? If I get a 0 or something there, that's going to be illegal. So you might have a matrix that's not invertible, so to speak. So you could check for that. We're not really going to run into any of that for these transformations, though. Okay, so let's talk about some of these special matrices or some specific matrix that we're going to want to work with, starting with the identity matrix. So again, this is sort of, you could think of like the number 1 in just our regular number system, but it just has 1s along the diagonal. All right, so if I do my matrix multiplication and I end up just taking dot products where I'm multiplying a bunch of things by 1 and zeroing out some terms, again, it's going to leave it unchanged. Okay, so that's the idea with the identity. This is probably what you want from a programming standpoint for your constructor to have initialize 1s along the diagonal of your matrix. Okay, so that's our identity matrix, the default. All right, so that's a good one to have. Let's talk about some of the more exciting operations that we can do. So scaling transformations. Start to get our things to move here and scale. So what's the scale matrix? Well, this represents basically, as it showed in the illustration, a way to make objects bigger, to scale the points. We're lengthening them. If you want to think about that, their distance away from the origin or wherever the middle of that object is. And you can see it's along the diagonal of a matrix here. So again, in 2D world, I just have an X and a Y dimension, and that's what I'm going to scale here. Okay, so here again, here's some examples for scaling or zooming. Again, that's where we would use this, right? To actually make an object larger or to maybe zoom in on something and think about it that way. This is actually a really good exercise. Maybe I'll make this part of the homework, but to zoom into wherever the mouse cursor is. Again, these are the types of things you get on graphics interviews. Again, I'm just stealing. Your homeworks sometimes are just interview questions I've had. So you'll be prepared, which I wish I had. I just got lucky, I guess, but and figured it out. So anyways, here's a few operations. So again, if you're going to have something, or rather quarter the size of something, right? Scale along the x and the y-axis, right? You can think about picking one of these points here and say, okay, I'm going to go halfway on the y value and then halfway on the x value. Again, brings me about here. Again, you just kind of intuitively know where this is bringing you. And you don't have to uniformly scale things, right? You can do it non-uniformly, right? So you got all your power here. If you want to have some object like wobble or actually make one of these diagonals based off of a sine function or something, so you can create some interesting effect of it scaling, or you hit something in the game world, make it move around. That's how you can do it. All right, so that's scale here. All right, let's talk about a few other operations here. This one's a shear or skew operation, so I'll at least just introduce it. It's kind of a funky one, where we're kind of taking like the top points and just stretching them while the bottom side stays put. But that's an idea, or you could do both again. But I'll show you at least one version here, a shear or a skew. There's different types, again, if they're of shears and skews, but we could start with this. And again, we kind of think of it like pushing an object sideways. So again, since we're just working with squares, as shown here, or quads, basically, in this class, we just think about, well, which axis do I want to push? Do I want to do an X shear, which kind of pushes things along the Y? So that's this Y column vector. Or do I want to do a Y shear, which pushes things along the X axis here? And then in 3D, we don't really care, but there it is. So anyways, easiest way is just looking at it as an example, an x shear operation. I'm basically saying, okay, take all the y points and push them. I'm going across the x-axis. Okay, that's an x shearing operation. Okay, so I'm pushing my clock away along the x-axis. And then, of course, a y shear. I'm stretching things across the y-axis here, so pulling them up. Now this side's not changing because these points are already zeroed or not going to change here. Okay, so again, that's why it's just sticking there. But that's the idea of a y shear. And, let's see here. And it is kind of an optical illusion. So a couple of times I'm going to draw little lines here just so you can see, like, we didn't bring this point, way far up or whatever, even though it's going to look like it is. But that can be a handy thing to do. All right, so some Y shearing examples. Again, this is going to be a 2D class, but I've been kind of playing around a lot because I know some of you are going to get excited about 3D, and you can fake these 3D effects with 2D, right? This is what we used. Well, not me. I wasn't even I didn't have to be alive during this time really, but graphics programmers basically were figuring out hey, let's fake 3D effects. So if you stare at this one, or maybe it's useful to even kind of stare at this, and if you pretend this is a wall or something, and you're just kind of looking along this wall, that's yeah, that's kind of looking pretty 3D there, right? We're starting to get some perspective here. So this is a trick of a Y shear. Okay, and if you kind of have that in mind, if you look at this here, which is some stone brick, and then there's some walls and stuff here, and I guess there's some different regions here from this wiki page, basically identifying well, if I do a Y shear, I'm pulling the world up, right? So that's kind of like if I'm looking up or looking down, if I kind of stretch or squash it in different ways. And that's the trick, in these old school games you could use to create some perspective of being able to look up or down, or feel like you're in a 3D world. So that's the idea. I thought that was kind of a neat application. There's other tricks you can do with shearing too. Again, you can, if you really get into it, these operations that you're kind of stretching and moving stuff around, you can actually do a rotation if you use these shear operations in the right order. So anyways, that's kind of what programmers were playing around with. So yeah, and we are going to do some of this fake, at least I'll provide at least some samples of fake 3D but in 2D world stuff, because I think it's cool with this math. So anyways, that's the shear operation. Okay, so that's pretty exciting. So let's get into rotation. So now that we can kind of stretch things, let's just go the full way and actually rotate the whole object here. That's our rotation matrix transformation. And we're going to kind of want to drive this one, right? We have the tools. I bet if I sat you down long enough with stuff you already know, or just the stuff we learned in lecture, you could drive this, right? Because we've talked about polar coordinates and how that kind of gave us a convenient way to rotate about things. So let's look at this example here. Or again, I've got my vector A here. It's already sort of rotated about an angle, we could think, right, from the x-axis. So I've got some angle here. And what we're going to want to do here is add some other angle here. Angle phi or phi here to rotate this vector and just produce a new vector here. Okay, so that's our goal. Let's figure out how we get that derivation to do this. All right, so where do we got to start? Again, polar coordinates, probably more convenient to work with, or otherwise just to know how do we go back from Cartesian to polar coordinates back and forth. So vector A has a magnitude, right? So it has some length here that we'll kind of want to know. That's how, again, stretched out we are, our length. So again, there's the formula. Again, just calculate the distance, right, using our triangles. All stuff we know, simple tools. And And again, we want vector b here. Now it is important, I'll touch on this note, that vector b is also the same length, right? We don't want to do anything else, I just want to rotate it, right? Right, if you move something around, like let's say I take this microphone, let me be careful with this calculator, and rotate it, right? You don't want it to like stretch or fly somewhere, right? So let's figure out what's going on here. All right, so again, and here's our basic tools. Right, we've got this conversion from Cartesian to polar coordinates here. And again, slow me down if I'm going too fast. I'll slow down a little bit during the derivation here. But again, our x point, just take wherever our radius or how far out we are and multiply by cosine. That's giving us, where we fall on the x-axis. Okay, so just intuitively, so we know these things. And then y, we're using sine. And again, I just remember those alphabetically. X, because cosine comes first, y, sine comes next. All right, what are we doing? We're rotating, okay. So what's that mean? I got to add some angle here, because I said, well, we had this angle A or alpha, right, if we're using the Greek term here, and I was going to add another angle to it to kind of get that rotation. What does that mean? Oh, these guys here. Okay, so I want to do this addition, and then out of nowhere I just threw out this formula here. Okay, where did this come from? And again, these are things probably somewhere in your life, maybe, maybe they're blacked out or something, but right, you learned about these like angle sum, formulas that somebody else had proved. And again, basically these are ways they're saying intuitively, using sine and cosine, how far along have I moved on the x and the y axis? Okay, based on some angle or some distance traveled on that unit circle. So let's take a look at these trigonomic identities. Right, they're proven things for us, but this is what we need to do if we add two angles together. All right, and then again, you can look these up. Here's the idea. We'll work with these to derive our rotation. I'm going to give you a moment to kind of stare at this. So, I had to look at this for a while, and somebody taught me this at some point, and then I looked at it again, and it made sense. Basically, if I have, this is what we're starting with, x and y, and we want to figure out, okay, where does that vector end up, right? We're doing our addition here, but we can use a sort of a substitution. If I have r cosine of something, right, some angle, right, I can figure out what that r cosine of something is, and I can replace that with an x in here. Okay, and then if I have an r sine of something with an angle, I can also replace that with a y in here. Okay, so I'm going to give you a few moments to stare at the sort of derivation here with the facts. Here, right, the top left is just our conversion of Cartesian to polar coordinates. Okay, that's all we're doing here. Again, that's just a fact, how we move from one system to the other. And again, the trigonometry is what kind of is tying together the Cartesian system with the polar coordinate system, which is neat. All right, so again, just looking, let's just focus on x and kind of stare at it for a minute. Right, I want to figure out this new value, x prime, where I'm going to land, right, after I rotate my vector by some angle here. I guess it changed, phi to a theta plus phi here, doesn't matter. And I say, okay, if I want to add two angles, here's my, trigonomic identity that I found in the back of the book that proves this. But really, again, it's just showing us if I move along, the x and the y-axis, where do I land? And then if I just do some substitutions, I say, okay, r cosine of phi, that's this funny one here. I'm just going to replace that with x and get x cosine of some angle. I'm going to replace r sine of phi here with a y and just get minus y sine of theta here. Okay, and look at that. I calculate my new x prime with this new angle that I have here. And then that's basically it. Okay, I've got something that I can do for calculating my new x values. And then independently over here, I've got something I can do for my y values. Okay, that's the derivation. For those of you who have started PSET 6, you'll see in part 1 when I give you a little demo, I just do this, manually for you, and like there's like a demo code that runs. And I do this with variables x and y and compute the whole thing. But, we shouldn't have to do that. I don't want to do this in 2 different places. I don't want to mess it up. I just want a transformation matrix, which is what we're driving here. So I could just say, give me, like in our factory pattern, a rotation matrix that's by this angle. And that's all I've got. Okay, that's where we're going here. All right, so again, just from the derivation. All right, so so we're basically going to take this form here, which you see at the top, with our new x or our new y, and convert it to this form down here. All right. Again, we're going to stare at this a little bit. Well, I should rather tell you this is the rotation matrix for 2D. All right, and I can kind of line things up here. Here's my x-axis. All right, so you can kind of see there's a cosine here, and then there's a sine here. Here's my y-axis. Again, there's sort of a sine here, and a cosine here. And that's pretty much it. Well, almost pretty much it. But something weird kind of happened here. What happened here? Wait a second. Was I just making typos in my slide? Well, not as far as I know. They happen every once in a while, but all of a sudden this sine value. I mean, again, if you look closely, all of a sudden I threw in a negative here. Why did I do that? Anybody have any idea here? Why did the sine get negated? Why, or maybe the question is, why if you Google and say, what's a 2D rotation matrix, does everybody just give you this one and say, use this? It's kind of a mundane, yeah.
I mean, it's the image of 0, 1 after rotating by theta.
Mm-hmm.
And, I mean, so minus sine theta is just cosine of theta plus 90 degrees. And then cosine of theta is just sine of theta plus 90 degrees.
Okay, yeah. Yeah, so we're going to work it out. And yeah, I saw the way, I was paying close attention to which way you're rotating your hands. That's the main reason we're going to think about this. Some of you are not along here, but just the rotation happens, counterclockwise if we do this. And if our screen's upside down, that's kind of the expected direction if we're rotating something. So then we kind of re-rotate it the other way. So you can not negate, or rather keep the signs here, but then your rotation's going to be clockwise. But then when we flip to the screen coordinates, then it's going to be counterclockwise, which might not be what we expect. So that's one kind of interesting thing about this. If you kind of search around and wonder what's going on here, it doesn't matter. This starts to get a little bit more important when you're in 3D world, because you'll end up rotating about 3 different axes, and you want to make sure they're all going like the same way around each of the poles in your 3D graphic system, or each of the basis vectors. Now here's another kind of interesting thing to think about. What's the length of the x-axis and the y-axis here? And hold on to this thought. You want to give it a try? Yeah.
Yeah, I mean, if I'm remembering the identities right, I think they're both 1 here.
Yeah. Yep.
Thanks.
That's good memory. Yeah. Again, these are things you probably saw in the back of a book. I think I mentioned it in one of my slides because it was the only one I could remember for a long time. But if we compute the length, right, cosine times cosine, and even negative sine times negative sine, etc. It is 1, right? This is an identity. Right, if I take cosine squared plus sine squared, that is equal to 1. Okay, of any angle, right? That'll keep us on the unit circle. Okay, why is that important? what is this, trivia hour or something? But no, it's actually really important in graphics. And again, this is the kind of stuff that'll, this is the kind of stuff that lands you the job because they're like, all right, this person studied graphics and game programming. But it's important because, we got this fun word. It means our vectors are orthonormal, which basically means that every vector has a magnitude of 1. Okay, now why is that important? Well, again, remember what we're doing here. If I've got this sort of x-axis and this y-axis, and it's telling me, where do I move or push some point, we kind of want to make sure that these lengths that I'm going to push this point are, say, 1 from the origin on both the x side and 1 from the origin on the y side as well. If we don't do that, then it's not very uniform, and we're going to get something that's like squashing or stretching or just moving all over the place. Okay, it's kind of hard to illustrate. Let me see if I might have a picture in some slides later, but if you just imagine a cube spinning. Or we don't have to imagine, right? Let's see what our prop is, right? Okay, here, the calculator is what we got on here. If I turn this, are the sides of one side getting longer or shorter or anything? Better not be, right? Otherwise there's some sort of like physical, like quantum meltdown or something. For those of you in the quantum computing class, but right, that's the idea, right? We don't want the dimensions of like one side on the axis like changing, right? It's just staying the same shape, same sides here. So it's preserving the ratios between each of the sides if the magnitude's 1 here. Okay, so that's the idea. That's what it means if we have an orthonormal matrix here. There's also another, and this is what gets you the bonus points when you start negotiating. Like, all right, you got the job. Now you're going to negotiate your bonus or your terms. You go to your employer and you're like, well, this is really cool that this matrix is orthonormal, but it's also orthogonal. So since I have something on the x and the y-axis that are perpendicular, the transpose of the matrix, does anybody remember transpose? I haven't put a slide in here yet for it. I'll give you the first go. Yeah.
Just like swap the rows and columns.
Yep, swap the rows and columns. Yep, and get an agreement. Effectively, but if I have a matrix that's orthogonal, all I have to do, and it's a really cheap operation, if I say, okay, all of a sudden cosine and sine, I just sort of swap them or turn the matrix sideways. That's the inverse of the matrix, right? Then I don't have to do all that determinant, nonsense and figure out, okay, is this dividing by 0? So it's really, really fast if you can do that. Okay, so for those of you who want to dig in a little bit more, that's where you say, yeah, give me the 50K bonus, not the 5K. But it's true. I mean, that saves a lot of performance. All sorts of cool stuff. So anyways, so again, this is basically, and again, to get the job right in the first place, we got to just know what the rotation matrix is here. You can kind of memorize this or derive it. Again, for the purpose of this class and your career, to be frank, you can pretty much just look this up always, but you want to understand what's going on. Transformations on the x, transformations on the y, and then you multiplying the point and then doing the dot product, and that gives you your new side here. Okay, so that's your rotation here. Make sense for folks? There is, if you dip into SDL, there is like a rotate function or something, but it's kind of wonky. We're going to kind of not, we might use it, but we're going to have to pretty much drive our own to do things properly. So anyways, here's some more rotations with the clock as an example here. All right, a few more transformations. So we've been able to, scale stuff, rotate things, use a skew or a shear operation to kind of push and pull some of the points. We can also reflect them. So again, if you want like a mirror or something, again, you can reflect across the y or the x-axis, or at some angle if you want, right? If these things aren't just 1 or -1. But again, the way to think about it is, okay, if I make one of these points negative, I'm flipping all my points. Let's see, flip flipping all my x coordinates because this is my x-axis. So I'm flipping about the y-axis. You'll see in a second. And flipping about all of my y coordinates flips it down on the x-axis here. So here's reflection about the y-axis. Okay, so I'm taking this original clock and kind of swinging it around on the y-axis here, so it's reflected, and then the x-axis reflection as well. Okay, so there's a couple operations here. Let's just think about something, right? We want to create some sort of game effect, something like this. Just take a moment, think about yourself. What kind of transformations might be going on here? You could pick anything in the scene, really. Take a moment to think about it. I'm going to give folks a chance to chat, too. And then I'll give you the first go, Mackie. All right. And if you thought about it just a little bit, maybe chat again with somebody nearby. Introduce yourself if you haven't already. Yeah. You folks can join up. Just find somebody nearby.
This is. Alright, let's take a quick show off. Yeah. It's like it's
and one by one, it's like
with the matrix.
then it's moving back and forth. It's like it's alternating. Like you see some parts of like your own. So I guess if you're going
you get the translation. That's seems like really fine.
Then they like a game object. Mirror of the character.
It's like you're. I mean, the reflection part is actually easy, right?
It's like it's not supposed to be a mirror. Actual effects of the guy.
the light. I think it's just like the light, like
One is like a
reflection.
It's like a series of shears. I don't know.
It's not like an actual.
Because that one just looks like it's like a
They
thing.
probably just
Scaling glass.
Sorry, because you just put a copy of.
It's funny because like, the trees are really good, and then you look at the dude, the reflection.
I guess
of the
the
dude,
flipping.
like it's like a green. What happened?
Yeah, he's getting a little bit. Something's going on. You can't tell who it is.
Yeah, you can't see any of the trees.
Yeah,
They like definitely like for the actual mapping. Sure.
Yeah, interesting. Yeah. Hold on to some of these thoughts. Will be interesting. Alrighty, so hopefully you had a little chance to discuss. Mac, I can give you what did you folks talk about?
We weren't as certain for the. Sorry, I'm a bit sick. We weren't as certain for the what's causing the ripples. I guess suppose it's taking like slices of them and then moving them back and forth. But as for the reflection effect, obviously not actually a reflection. It's just like doing a mirror image, flipping of each individual sprite that you want to appear in the pool. So like for each tree, you just create another tree, just below it that's upside down.
Yeah.
And that'll be on like a sprite layer below the grass.
Yeah.
The one the player can move according to the player's position,
Mhm.
but that would also just be like a separate sprite from the player's sprite.
Mhm. Yeah, so touching on a bunch of interesting stuff here, right? Like I'll just mention a few things, right? Like there could be some like taking the trees, and I think as you mentioned, like just some of the ones that you want, flipping them, right? Maybe not necessarily everything, and either pasting them in here somehow, and then we're not sure how like the wavy effect necessarily works, right? But we could take some guesses. Copying some of the game objects. You talked about the draw order too, which is going to be sort of important here. I like all these thoughts. And reflection and some of these things, the transformations. What did other folks talk about? Other thoughts? Yeah, it's kind of interesting to think about. I mean, there's a lot of ways you can do this, and again, it depends on how you want to think about it, right? I mean, maybe they just duplicated the whole scene and then like flipped it or something. That might be a little bit wasteful. Then we got to kind of remember some of our other things we learned about, like bit masks, and just kind of saying, well, yeah, get rid of all these pixels that don't land on the water or something, and do like a and out all the pixels there, zero them out. Maybe there's a sine wave going on here with the pixels. Maybe it's a shear operation. Maybe it's a rotation. So yeah, I mean, part of this is one just to think about transformations, draw order, some of the stuff that we talked about. But it's also just a little bit of an exercise, right? Because we're not too far away from the final projects that, you'll want to just get some inspiration and just kind of look at a game and be like, how did they do that? How do you create water or mirrors or these types of things here? I mean, it could be as simple as, maybe they copied the whole screen and said, okay, somebody mapped out these are the water tiles and they're going to do some like cool effect. Maybe they duplicated the game objects. I mean, there's a bunch of different ways to do this. So I'll take any answers you folks have. All right. So I gave a few, ideas. If we go in graphics card land, right, maybe we have shaders for my graphics folks who have done that kind of stuff, which can do these effects. But you still got to figure out, where you're drawing stuff, the draw order, and the transformations. It's all kind of interesting things. Okay, so let's talk about, one of the the expression, the elephant in the room, right? What's missing here? We haven't figured out how to move points yet, which is translation. Okay, so I want to move some object. Now, of course, we've just been sort of doing this, right? We just say, well, let's choose this XY point, and then choose another one, and it, moves. And in screen coordinates, that's fine, right? We can just kind of move stuff around. But, if I rotate something, again, I don't want to just guess where the X position is. I'm going to, move something else. Right? If I'm turned 45 degrees and I want to translate forward, what does that mean at a 45 degree angle? So a few sort of keywords to know about here, or the sort of math, right? And these things always sound a lot scarier than they are, so I try to provide some definition. But the transformations we've been doing are, in a branch of mathematics. Basically, it's called affine transformations, which basically says it preserves ratios and distances. Okay, so again, the story with rotation, points as we're rotating on the same shape are exactly as far away as they were, before and after the rotation started. Okay, that's all it's basically saying here. Okay, so we want to preserve something about, distances between points here. Okay, so that's the idea here. So what actually ends up happening, though, is if we want to perform a translation, that is to find some new point here on the left side, x prime or x2, whatever you want to call it, right? I can't actually translate this object and have some sort of guarantee about preserving ratios between them. Okay. So how do we get around this? Well, the trick is we just cheat in 2D graphics. We do the same thing. We cheat in 3D graphics for the most part. And we basically just say, well, why don't we just add another column vector here? We'll have our X where we want to translate, our Y where we want to translate. And I'll talk about this one point here. I'll just put zeros at these because that's not going to really change anything. But basically that gives us some sort of storage you could think of in this data structure, this matrix for the translation, right? You can almost think about it, for those who watch the 3 Blue, 1 Brown, I think I got the order right, series on Essence of Linear Algebra, right? You can almost think of this like you're shifting the origin of your coordinate system to this point here, which is kind of neat. So anyways, that's how we can kind of think about it. I'm going to leave this 1 here for a moment here. Y is, and this is going to be labeled W here. So X, Y, you'd have a Z in 3 dimensions, and then W would be the next thing here. So X, Y, and W in 2D. Okay, so what I'm basically saying is, okay, if I take this here, X, Y, and again, I'm just putting 1 at the end. This is some point that I want to translate or move, right? Because again, a quad with our sprite has 4 points on it. I multiply it by this special translation matrix, and it's going to give me a column vector here with the translation, okay? With the appropriate how much to move on the X, the Y, and then the translation values, okay? Or rather, how much I've scaled along this diagonal. That's why there's M1, 1, and so on here. Okay, so that's the idea here. Okay, so it makes sense. Folks buy into at least we added another dimension. I'm promising to you this is the right, translation matrix that we have. Hopefully we believe that. And then, throwing another point to homogeneous coordinates. So we have affine transformation. So basically it says we preserve ratios. That's this here. There's a nice video talking about it as well. That's the idea here. Okay, so let's talk a tiny bit about this last coordinate here, W. Again, another, and I remember, in my undergrad, my professor, he just told me, yeah, just make this thing 1. We asked him why. I don't think he knew. It took me a while to figure out why, to be honest. So I'll try to give you some intuition at the least here. But a few things here. Okay, last coordinate, why is this point 1 here? Okay, this final point here. Well, the first thing, it has some sort of meaning, at least in, let me go back here. In this example here where I have X, Y, and 1 here, okay? And I'm going to tell you this is a point here. If I have a 1 here and it's a 0, if it's a 0, then I have a vector here. Okay, so then I know if I have a point or a vector that's, that I'm moving around here. And what's kind of interesting is, do folks remember, could I add a point and a point together? Was that allowed? No, yeah, I'm seeing head shakes no. So it's kind of an interesting thing here. If I look at the math here, and let me just write this on the board so we can keep it straight. Let's say I have, I'm just going to do X, Y, 1 plus X, Y, and 1. Okay, I'm just going to cross this out. This isn't allowed, right? I have X, Y, 0, and X, Y, 1. I said 1. Let's see, can folks read this? Is this high enough? Okay. 1 is a point here. Okay, so this is kind of an interesting thing here. So 0 is a vector, right? Something with a magnitude and direction. So let's say this is me, right? And you're telling me how to get to Boston. This is the vector here. If I add these up, if I have a point and a direction, and how do I add vectors? Just component by component, right? So X plus X, Y plus Y, 0 plus 1. That's legal, right? So I get a 1 there, which is kind of nice. And since I end up with a 1, let's again complete this example. Let's see, this is going to be Mike here, right? And I land somewhere here. This is the vector V, right? I ended up with a 1 here, a new point, right? A point plus a vector. So the math kind of works out, which is nice. And then if I do the same thing, right? If I add 2 vectors that have zeros, well, we can add vectors, right? We know we can do that. So that's the one like nice thing. Mathematically, it works. And again, since we know this property, right, we can go in D and put a constraint or something and say, hey, if that W is, 2, we might want to check and, be careful. It's not the full story necessarily, but we might want to be, careful with what we're doing here, okay? Okay, so that's part of it. Let's see here. Where's the rest of my story? Okay. And it's kind of, to show it or an example in 3D. I don't really want to jump into 3D land, but it kind of makes sense. But you can kind of think of W as if I'm putting a projector on a movie screen, this W value is kind of like a distance or something that I'm projecting onto a projector. We end up using this W value for something called a perspective divide here. Okay, what's that mean? We're kind of getting in the weeds here. But it kind of means, we've got these properties that have to hold, right? We have to preserve distances and ratios. So let me give you another analogy. You're taking the Amtrak or the train like I do. You look down the railroad tracks, and the railroad tracks kind of converge, right? If you look down, but in truth, right, they better not converge, right? They better be the same distance. So we need some way to kind of, create perspective, and that's what the W will actually help us with our camera, where we can say, okay, objects that are really, really far away, maybe we can, through our camera, once we introduce that, divide things by some number so they get really, really, really tiny as they go far away, so they converge, okay? So that's going to be kind of the idea. That's where W comes from. But we need it to preserve ratios between distances like train tracks, okay? That's the idea. That's why we need W. How W works with points and vectors to sort of preserve this property. So if we're talking about a point that could converge over space, or are we just talking about a vector that's something that has a magnitude and direction? Okay. So if you want to hold on to one thing, or for folks on what is W, this is a really good talk. This is at the Game Developers Conference. This will again sort of explain the W and a point versus a vector. But it also sort of shows, kind of with nice visualizations, same as the 3 blue, 1 brown does, of like, what does it mean when we're transforming something? Well, we're sort of changing our basis vectors of where we're moving along, okay? Make sense for folks? Maybe you have some intuition or know where to look, right? That's maybe a question I would ask. Why is W1 here? And again, these coordinate systems, there's all sorts of them, and they all kind of mean the same or similar thing. What they're trying to tie together, these fancy terms, right? Homogeneous coordinates. But it's basically saying, and this is, again, for the example, homogeneous coordinates, this is basically why we add the W. Again, think of it like a movie projector, right? You're watching... I was trying to think of the last movie I saw in theater. I think it was Dune 2, but you're watching Dune 2 on IMAX, right? A really big screen with a really big projector. But if you move that projector closer or go to a smaller movie theater, right, there's this magic W value, or not magic, right? We don't want it to be magic. There's this W value that I can divide, and we'll see the same movie, right? It might be on a different screen, but the characters on the movie screen are going to look the same size. Does that make sense? All right. Hopefully that makes a little bit of sense. We'll need it for our cameras. That's why we're learning some of this math. It'll make our lives a little bit easier. Okay. Here's kind of a nice visualization of it as well. Okay. Just to, again, what is this W? Right. I threw out this other term, perspective divide, which I'm guessing is new for anybody who hasn't taken graphics. But if I have this point 2, 3, 5, and I say, okay, I'm going to divide them all by 1, 2, 3, and 5. So 2 divided by 1 is 2, 3 divided by 1 is 3, 5 divided by 1 is 5. Okay, we get that. But if I take this point here, 4, 6, and 10, and I divide those by 2, 4 divided by 2 is 2, 6 divided by 2 is 2, 10 divided by 2 is 2 as well, right? So it's effectively the same if I just look at these first 3 points and they go through this perspective divide. Okay, and that's me with my movie projector cart pulling it backwards, right, for the W value. All right, make sense? If I could move that projector, we could do it live. All right, so here's the W, and it's 100 feet or whatever. All right, make sense for folks? All right. All right, so I'm going to skip these. These are all sides, but basically the same example over and over and over because, again, that's how I have to understand things. So. All right, so for perspective, right, we're going to want perspective. We're going to want a fake 3D perspective at some point here. All right, so that basically gets us to the end here, right? We've learned about our math transformations. What was, again, the whole point of this? Well, matrices compose. So now I can translate something, rotate it, scale it. I can add a camera that has perspective, right? So for those of you who are playing games and want to know, okay, why is this thing have like an isometric view or some like cool like 2D effect where it looks 3D? We can do that now, right? We can actually use matrices to move things. For those of you who don't care about graphics, but maybe you're in like robotics or something else, this isn't animating. I don't know why, but right, if I have like an arm or something, right, I gotta extend the arm out and then rotate it or whatever, right? That's a series of transformations that we want to capture. So next class, it is going to be next class, we'll figure out, okay, what's the data structure that we need to represent these things if I've got, game objects, right? How do I compose these transformations? All right, so I'll move that to the next one. So that's it. I'm going to hang around for office hours if you have questions on any of this math stuff or other things going on. And don't forget your in-class activity. Should be up and running. All right, thanks, folks. We'll see you next time.
Thank you.
All right, SDL stuff. You can set your laptop up here if you want.
So I set it up in my frameworks.
Yep.
And I did give it permission to open.
Okay.
Let's see.
Let's see. Try.
I don't know.
If you click on the versions thing, click on
Versions.
versions folder, and then click on, I think it's A, is that what it is? That one. Try right-clicking that guy.
Very nice.
Open. And see if it asks you anything. Okay, that's fine. Okay.
But even though I was able to open that version, whenever I try to do through here, it won't let me do it.
Okay, can you do show in folder? Do it again.
Oh my god, Jesus.
Just keep doing it till let's see the show in folder again.
I think it's this one.
Try it again. See if it brings you somewhere else. Oh. Oh, it just keeps popping up.
Yeah.
Cannot check it for malicious updated. Okay, hit OK.